a real lab. So we're gonna use just simulator, okay? So we're gonna simulate any circuits that we're gonna implement in real world in the lab on any simulators that enable us to do so. And one of these simulators is Multisim, okay? I told you in the beginning that we may use Multisim, and I say may because maybe one of the components that we need to experiment with is not implemented there. There is no model for it. Then at that time, we're gonna search for another simulator that you have access to implement the experiment, okay? So till this moment, which is the first moment, because this is the first lab, we can do our today's lab in Multisim, and I think also most of our labs we also will do in Multisim, okay? Until further notice, we're gonna use Multisim, okay? So the first lab today is basically the basic outcome is to how to use Multisim. If you didn't use it before, you're gonna learn how to use it, how to open it in virtual computer lab, okay? How to save the projects, how to locate the elements or the devices that we're gonna experiment with, how to use the oscilloscope inside Multisim, and most importantly, we're gonna use a technique, okay, by which we can measure a characteristic of some devices using the oscilloscope, okay? So let me give you an introduction. So today's lab, we're gonna basically do something that you may see trivial, but this is also my intention to make it trivial, which is Ohm's law, just to avoid any mistakes in connections and stuff, and concentrate on the main objectives, is how to use Multisim efficiently, okay? And also the techniques that I'm gonna teach you today, okay, which is using the oscilloscope to measure the characteristic of any device. Okay, so we have 3 experiments today, okay, 3 experiments. So we're gonna use Multisim. The main objective is to verify Ohm's law, which is very basic, that V and I just changing like this. And the slope here is just the resistance, okay? If you increase the resistance, then you're gonna have something like this, R1 and larger than R. If you decrease the resistance, you're gonna get something like this, R2 less than R, okay? We're gonna verify it in 2 ways. The basic way that just come to your mind, okay? And here is experimental verification. So this is measurement. So we know theoretically that the relation between voltage and the current on any resistor is just linear, okay? And we wanna verify this experimentally, do experiment to show this linearity. So the basic is just to create a table, something like this. Which is V and I, and construct a very simple circuit, something like this. Put here a meter to measure the current. Put here a voltmeter to measure the voltage, okay? And we have here our E, and we have here our R. And of course, I is flowing through the R in that way. Okay, so what you're gonna do is just changing E. So for example, 3 volt, 6 volt, whatever, 9 volt, 12, let's go in this series, 15, 18, okay? And in each time measure the current. Then you draw, this is what we're gonna do. You're gonna draw it yourself with a hand and submit this in the report. Okay, next week. So here we have I, here is we have V, and we have these points. For example, at V equal to 3, whatever, or you know, we get this current, for example. We'll make it V and I, whatever. Okay, so at V equal to 3, we have this I1, for example, just a point. At V equal to 6, we have this current, you know, and continue in the same way, and then draw these, you know, these dots together and measure the slope. In that case, because I in here, because I here is a follower, variable, okay? Or the dependent variable, we can say. This is V now because we change V, is independent variable, okay? So always we put the independent variable on the x-axis. So y is function of x is independent and y is a dependent. So in here, v is a thing that we change, is a variable that we change, and based on its change, I will change. So I represent y, which is the dependent or the follower, and v is the independent variable. Okay, and in that case, slope here will be 1 over r. Okay, very basic stuff. After that, we're gonna learn another. So this is the basic technique. Okay, step by step, point by point. Then the other technique is using oscilloscope. You guys all know the oscilloscope. Anybody here don't know oscilloscope? You should have already experimented with it using in the circuit theory course. Anyways, if you don't know it, I will show it in our lab today. Okay, so in that case, we're gonna show the oscilloscope is something like this. Okay, that has some screen, you know, some, you know, controls. So we're gonna show this. So if we have a resistor like this, and this is the voltage, we're gonna show the relation on the screen on the oscilloscope. We're gonna do the same thing for some devices, okay, that we're gonna take in future lessons. For example, tomorrow, and for example, something called the diode. Okay, this diode is a device. Okay, and we're gonna measure its characteristics using this technique, using the oscilloscope, because it's much more convenient. Okay, and much more precise also, to avoid any, you know, handcrafting errors in drawing the curves yourself. Okay, so let's start. I will share now another screen, not that one, and you must now bring the lab manual that or sheet that I shared with you in front of you, and just follow me in the steps that I will do. So let's now share this screen. I made some minor changes in this file. Okay, you guys can see my file, right? The screen.
Yeah, we can see it.
Good. So where is this guy? So here is learning outcomes, okay? And here is how to implement the first circuit. We're gonna first, I will do is use a step by step, okay? I will show you just a few points, but you will do the measurement yourself. So I will do some steps with you now. Then I'll give you, for example, 15 minutes or something to do the points, all the points, it changes the voltage and measures the current and draws a curve, okay? Then we're gonna go to the next experiment and so on. So these are the steps to open Multisim, okay? So you don't have it on your computer, but we have it in virtual computer lab. So we're gonna just go to this link. Escape verification. Load its opening. Then click on virtual computer lab. This link in here. I mentioned that in the Word file. Just click here. Okay. Let's keep that with us. Okay. It will ask you to log in using your CSUE credentials. It should be, yes. Everything is fine. Yes, and here we go. Here is all the softwares that you can use in virtual computer lab. Okay. So and one of them is our Multisim. Here is it. You can search for it if there are many here, so you can search like this, Multisim. Then it will give it to you. Okay, so this is Multisim. It's from National Instrument. Okay, you then just click launch. Everybody can log in.
Yeah, just loading up right now.
Good. If any of you has some problem, just let me know as soon as possible. Okay.
This is recorded.
What, Roshan?
Is this lecture recorded?
I didn't understand as usual.
I'm saying, is this lecture being recorded so anybody
It's
can look at it
recorded,
again?
yes.
Yes?
No, it's yeah, you should, yes, of course it's recorded, but you should follow me, okay?
Just following. Thank you.
Very sorry, guys. So the phone just went crazy and started calling people. Okay. Oops. Okay, that's fine. Okay, we have virtual computer lab. I'm sorry, Multisim right now in front of us. Okay. Here you will find some of the devices that we're gonna use to, measure stuff, measure currents and voltages, oscilloscope. Okay. So, and we're gonna explore these steps together as we go in this lab. Okay. This lab and of course following labs. This is now the name of the project. Okay. You can change it later or now, whatever. Okay, I put this also in this in this manual here. Okay, so it's loaded. Now let's construct, this very basic experiment with a voltmeter here and I'm sorry, with a battery here or a voltage source, and here is we have a multimeter, okay, which is much better than using. You have also voltmeters that only measures voltages, but it's more convenient to use multimeter because it gives you all the stuff you want: voltage, ampere, and also a resistor. Okay, it's a multimeter. Here is another multimeter, but this guy will behave as an ammeter. So I set it to measure current. This one is set to measure voltage. And we have here a resistor, okay, which is 1 kilo. So let's construct this. So basically, you click on place, and choose component, okay. And I'm just following the lab manual with you. So in the family list, this is a family list, as you see here, okay. Just navigate down. It's sorted alphabetically. So you have the A's and B's. Anything start with A, okay, then anything start with B, and so on. So our stuff is resistor, which is started by R. So it's going down. Resistor, yeah, this guy here, okay. Then you kind of choose whatever value you want, okay. Let's have the 1 kilo ohms, the default one. It doesn't matter. And just click OK. Put it. It will bob again this window. Okay, so you just click OK. That means, I'm sorry, close. That means you are fine. You are fine now, and you have all what you need. You don't want extra components. It's look ugly in horizontal, so we can also change the orientation. So just right-click on it and rotate, 90 degrees, okay, something like this. Good. So we have our resistor now. Again, we now need what we're gonna need also. Yeah, the DC power source. So go to the same. So we are now step number 7. Okay, the rotation and clicking the close or whatever, all of this is mentioned in the steps after number 2. Okay, so place again, component, then also go to family, and now choose from family, choose what? Choose power sources. So it's B. Yes, power sources. Where is power? Yes, this guy, power sources. And we have DC power source. In our circuit, this circuit here, we have a DC power source. Okay, so DC power source, and then click OK. We'll have it. It will move again. Just click this. Okay. Now we need 2 multimeters. Okay, we need one here to measure the current and one here to measure the voltage. The multimeter should be here. Where is it? Insert 2 multimeters from the rightmost list. Yes, this is the rightmost list. So I think this is the first component, which is multimeter. So we're gonna place one of them here and another one here. Yes. Good. Now we're gonna make the connections, the wiring, okay? And this is very easy one. So here, just to hover over the symbol, okay? And this, I don't know how to describe it. You see the difference? So this is away from the symbol. If you hover over it, then it will change, okay? This means you can make wire now. So we're gonna connect the positive of the voltage source to the positive, and watch out here, of we can, yes, we can do it in that way. Just to avoid the crossings. To the positive of the voltmeter, and you can connect the negative of the voltmeter to the negative terminal of the multimeter. Then you make this connection here, the positive, because the current is flowing in that way. So we need to connect the positive to the positive of the battery, and the negative to this terminal of the resistor, and this terminal again to this. We just lack one thing here, the ground. And the ground can be taken out or placed from the same place as the power source. So go to place again. I think this slowness because we have many, licenses are working at the same time with the same computer. But anyways. Okay, so go to components. Yes, so there is ground here. This is the ground. Click OK, and have it here, okay, and close. Okay, and it's connected. How could you know it's connected? Just left click and try to move. When it moves, it will show that there is a connection. So you are fine. It's connected. Okay. So now we have this circuit in here. Okay. Although that's much more neat. Let's try to make it. Yes, that's nice. It looks nicer now. That's good. Okay, this is our circuit. Now we're gonna we're gonna change the voltage, okay, and measure the current. Okay. So you can choose whatever values you want, okay. I suggest, for example, 3, 6. This is one of the ones that I did. 3, 6, 9 just goes in that way, in that series. 3, 6, 9, 12, 15, for example. You have 5 points, okay? And we will measure 5 points of the current, then draw them together. So, for example, let's start by 3. To change a value of any component, just right-click, left or right. It should be written here. Yes, double click. But of course it's very slow because of the licenses. And I'm very sorry, this is not my fault. But anyways, okay. So it pops up now. It's really slow. Session disconnect. Okay. Good. Okay, 3. And just click OK. So we now have the voltage at 3. Okay, and the resistor is 1 kilo ohm. So what we're gonna expect the current to be? The current will be, 13, 14.
Just 3 milliamps.
Of course, 1 milliamp. Okay. Okay. Now we're gonna run the experiment. Where we run? You can run from here. This little symbol here. This means run. And just hover over it. It will give you the hint. If you wanna run from me. Click me. But formally, you go to simulate, and you just find the same one there. Do whatever you want. It's both equal. Just a shortcut here. Now we are running. Okay, so now the circuit is running. So if we click on the multimeter, we should see the current 3 milliampere. Of course, this is an ammeter, so I just set it to ammeter here using A. Just click here, and we are measuring DC. And this is a voltmeter, so by default, it's a voltmeter. So just double click. So it's a voltmeter, and it's measuring 3 volts. Okay, good. So now we have 1 point in our curve. Okay, at 3 volt, we have 3 milliamps. Now we're gonna do 6, and 9, whatever. Do whatever you want. Just, have yourself doing it right now. Choose any points you want. Okay, I suggest 3, 6, 9, 12, 15. And then draw the curve, and this curve will be part of your report. Okay, so it's just a paper and just throw it. No. So do it now, and maybe after 10 minutes. Okay, let me know what kind of curve you have. Should of course it should be linear. Okay. So you have, guys, 10 minutes. If you all finished, just let me know. If you have any questions, something you forgot or something, just ask me.
Yeah, Professor, we're seeing the lips move, but you're muted, so we can't hear you.
I'm sorry. I'm very sorry. So somebody has a question here?
Yeah, I was just wondering, we're plotting the graph on paper, correct?
Yes, yes. Yeah.
Okay. Awesome.
I will search now for a tool on the internet. Maybe there is an online tool or something that you give it the list, the table,
Right.
VI, and it draws or plots the graph for you. But just keep going. I will search for you.
Okay. I mean, we could use it on Excel if you want us to plot the graph.
You can what?
Microsoft Excel. It's a program.
Yes, yeah, of course. Yeah, Microsoft Excel. Yeah, yeah, I forget about it. Yes, yeah, do it in Microsoft Excel. That would be much better. Yes, please. And of course, Microsoft Excel will give you even the slope, so you can measure exactly the current. I'm sorry, the resistance. That's very nice suggestion. Thank you. Good. So you guys be sure to repeat this at 1 ohm and 2 kilo ohms in your report. Okay. So I want 3 plots. And in these 3 plots, you're gonna determine the slope. And Excel will do everything for you. Excel is very nice, very convenient. Just draw and search for some options there in Excel. If you didn't find it, just ask Google. You will find features in Excel to determine the slope. And it should be 1 and 2 kilo ohms. And of course, the first one 1 kilo ohm, so 3 plots. Now, we're gonna save what we have done. So just create in this virtual lab is it's open for everybody, so you can save your project. So just from file here and save as. Okay, just to like any. And create a folder with your name. Here is my folder. I created a folder for my name, Mustafa Abderrahim. Just create a folder for yours. Just open this folder and choose any proper name for it. Something descriptive. Okay, like for example, Ohm's law verification step by step, something like this. Okay, anything descriptive for you. I already have it, of course, so I will not do that. Okay, so let's now go to the second. Yeah, this is what I'm saying. So let's now go to the second technique to measure the characteristic. Okay, the technique that we actually will do with diodes and transistors and stuff. So I will share the other screen right now, the OneNote, and let's see how is this gonna work. You guys can see my OneNote, right?
Yeah, we could see it.
Good, good. So how to measure the characteristics using oscilloscope? So basically, this is the circuit we have. We have a resistor. We have a voltage source, okay? And we say that we're gonna change the voltage and we're gonna see a current. And we know for Ohm's law, it should be something like this. And the slope here, 1 over, because this is I and this is V. If it's the opposite, it will be R. Okay? So that's what we want to do, to draw it automatically. Okay, we don't want to go in this tedious, steps of, one point by one point, okay? And for linear, it may be okay, but if it's the relation is non-linear, okay, and we will do that tomorrow, we'll see tomorrow in our lectures that our device is usually non-linear, okay? So you may mess up when you draw the curve and get a curve that is not, close enough to the real characteristic of the device that you are experimenting with, okay? But oscilloscope will give you something very precise, okay, to the device that you are that you want to know its characteristics. In here, it's a resistor, which is Ohm's law. Okay, so what we are doing basically in is we wanna for each point in V to get a point in I. For V1, we want I1. For V2, we want I2, and so on and so forth. And if we increase the number of points, that will give us a very close characteristic or curve to the real characteristic of the device that we are experimenting with. But the problem is that if we do many, then we will take longer time because we change step by step, as we see in the first experiment. For each value of V, we showed, double click, change the value, run again, read the multimeter, the current and the voltages, and, draw the curve. It's very tedious, okay, to get many points. But the oscilloscope will do that for us. So the oscilloscope so what we only need is something that makes the voltage vary, okay, and at the same time measure the current while the voltage is varying. Good. We know that if we have an oscilloscope that have, for example, two channels, the channel A and the channel B, and you have a sinusoidal source like this, or any source, any variable voltage source, okay, and you connect the positive, for example, with this terminal and the negative with this terminal, okay, the oscilloscope, this neat device, will draw in its screen exactly the signal that you have, V. Let's call it V input, whatever. Okay, that's good. That's very nice. And we know also that oscilloscopes cannot measure current. That's a very that's a problem, but we'll get around it. Okay, so what we actually need to our oscilloscope to do is to draw the voltage on the screen and draw the current on the screen as well. But we can't measure current. Okay, that's a problem. So what we're gonna do is a very nice trick. So we'll use another, we know that from Ohm's law, we know that V is equal to IR. So I is equal to V over R. If R is equal to 1 ohm, then I will be equal to V. So if you have a circuit like this, and this resistor is 1 ohm, and here is some voltage source, whatever its value is, and you have an oscilloscope, let's call it CRO. Oh, this is okay, strange abbreviation, but they do it like this. And we connect the positive here and the negative here. Then what we're gonna see in the oscilloscope screen is if V is, for example, a sinusoidal like this, we're gonna see also a sinusoidal wave, which is the voltage of this resistor. But since the resistor has a value of 1, then this is also can be considered as the current. Okay? Good. So to measure a current, we can just plug any resistor, okay? Draw the voltage upon this resistor, then divide by the value of the resistor, you're gonna get the current. And the value, if the value of the resistor is just 1 ohm, then you have it. You don't need even to divide. But if it's, for example, 2 ohms, then if you want to know the current, just take any value here and divide by 2. That's it. But if it's 1, then it's okay. You can just take the value, this is the current. At the same time, it's voltage. Good. Now, how are we gonna use this trick in order to do our experiment, or in order to draw the voltage, you know, the Ohm's law on the screen of the oscilloscope? Okay. So let's do another one. So what we're gonna do is to use a resistor, another resistor. So let's erase this. Another resistor, other than the ones that we are interested in. So for example, if we have basically originally 1 kilo ohm, this is our basic R, then we have another, we will get another resistor which is just 1 ohm, for example, okay, to apply our trick. And we have our voltage source. Good. Since, let's call this RP, for example, whatever, call it whatever. Since RB is much smaller than R, then most of, if we call this VR, and if we call the voltages here VRB, so VR will almost equal to V, and VRB will be negligible, okay? Just by voltage divider, this is voltage divider. VR is equal to V multiplied by R, which is 1000 over 1001, which was equal, almost equal 1. It's 0.99, something like this. So VR is almost equal to V. Very nice. So if we connect, yes, if we connect, I'm sorry, I'm just messed up here. This is experiment number 3. So don't worry about this analysis here. I will just erase it and do it in a direct way. I'm very sorry. Okay. So this is the last point we stop there. Just forget what I explained. So if we use another resistor, okay, which is have a resistance of 1 ohm, okay, we're gonna use the oscilloscopes that we have and connect. So this is the oscilloscope now. It has 2 channels, okay, A and B. We want to measure the voltage over R. So this is the voltage over R. And we want to measure the current also that go through R. So this is positive, negative. Okay. So we have now an oscilloscope with 2 channels. One of them is connected to the resistor, which is our interest, the 1 kilo ohm that we started with. And the other channel is connected to RB, the other resistor, which is equal to 1 ohm, which you put to measure the current indirectly. So now on the screen of the oscilloscope, we can see 2 signals. So if V, for example, is a sine wave like this, the screen of the oscilloscope will have 2 signals just upon each other. So let's draw it. So for example, this is V or VR, okay, and with another color, for example, red, and this is VRP. But since RB is equal to 1, this is also IRP. Okay, good. So everybody is following me? Everybody on the same page? If anyone, if you have a question, just let me know. Let's proceed. Okay. If anyone has a question, just let me know. Okay, let's proceed. Remember, our main goal is to draw this linear relation on the oscilloscope. All the oscilloscopes have something called XY mode. What happened with this mode? In this mode, the oscilloscope will not draw the 2 signals he has on channel A and channel B. No, it will not do that. It will do something very useful. It will actually draw them together. So it will take, for example, the signal on channel B and put it on the x-axis, and the signal on channel A and put it on the y-axis. Then, at each time, let's now have another color. This is, remember, this is the time. Okay? So at each time instant, it will take what it does, for example, at t, for example, it will see the value of the red curve, which is the current. Okay? And is a value which is B, and is a value of the blue curve, which is VR, which is A. So you have 2 points, one on X and one on Y, so you can make a point. Then at another time, for example, let's call this T1. So at T1 we have I1 and VR1. At T2, it will do the same. This is a value of IRB, let's call it I2. And this is the value of VRB. VR2. I'm sorry, yeah, VR, not VRB. Another point. And so on and so forth. And even for the negative. So in XY mode of the oscilloscope, if you have on the channel A, VR, and on the channel B, VRB, which is equal to IRB, okay, and you choose, without XY mode, you will see just two sine waves on top of each other. But if you set the oscilloscope in XYB, and sometimes they call it AB mode or BA mode, oral equivalent. But in BA mode, that means that's different from AB mode, in which signal will be on the x-axis and which signal will be on the y-axis. That's it. So both are the same, but we just flip the axes. Flip the one that makes that will be on the horizontal axis and the one on the vertical axis. Okay. So since this is, you know, an Ohm's law, we will expect that the relation between the voltage on I on the resistance R, which is VR, and the current that flowed through this resistor, which is IR, which is, let's call it I, we expect the relation to be linear, which is Ohm's law. And we expect that the slope will be equal to R, which is 1 kilo ohms. Okay, guys? Please, if you see this is difficult or, you know, something is missing, even if everything is missing, just let me know. Okay? If it's clear, we're gonna proceed. But please, if you have any question or any confusion, just let me know. It's not straightforward, but it's very useful because it will give you the exact characteristic just on your screen. And you don't need to take such many points in the manual mode or step-by-step mode that we just did, you know, in our first experiment to get good or more precise curve. And you don't need to draw with your hand. Okay. So I will recap it again very quick. If we did this circuit diagram in here, this circuit diagram, oscilloscope or CRO with 2 channels, and connected channel A to the resistors that we're gonna measure the relation between the voltage and the current through it, or verify Ohm's law through it, okay? And connect channel B to another resistor that we bought, okay, which is 1 ohm. Then basically, in the normal mode of the oscilloscope, you're gonna see 2 signals. And we must put here a variable signal, because we want automatic drawing. So we want the voltage to change by itself without our, you know, without our intervention. We are not doing step by step. So we're gonna choose, for example, sine wave, because it gives you many points. Good. Now we're gonna see the first signal, which represents the voltage across VR, and the second signal, which is the voltage, which is B, the voltage across RB. And since RB is 1 ohm, then this signal is also the current. Now we switch to something called XY mode. In our multisim, you will find it something called EB or BA. That means, draw, for example, for AB, for example, both A, draw the 2 signals together with each other at each time instant. So for example, on A, we will put the signal on A on the vertical axis, which is VR, and the signal on B, which is IRB or I, whatever we call it, on the x-axis. And at each time instant, we take the two values and we just make a point, because each point here on this curve, on this line, has two indices, x and y. The x comes from the I, the voltage on RB, which is 1 ohm, and the Y comes from the VR, which is the voltage across our main resistor, the one that we started with. Okay, and this will draw for you the Ohm's law automatically, without any step-by-step procedure. Okay, so let's do it now together, and again I will let you to change. Now, since the oscilloscope will do this for us, you just need to include in the report a snapshot. Okay, just draw whatever on Multisim. The oscilloscope will give you some shapes, just snapshot and put in the report. Okay, but still you have to measure the slope, and I will show you how to measure it. Okay, so let's switch the screen to our Multisim screen here. Screen number 3. Now you can see Multisim, right? Someone say right or no? Good.
Yeah, we can see it.
Good. Thank you very much. Okay, so experiment 2. Verifying Ohm's law automatically using AC source and oscilloscope. Okay, so let's just let's save this. Okay, that's fine. Let's save it. Save as. And here let's say lab 1. Just x1 repeat. Just to differentiate between the ones that I have and this one. And once you do this, it will change by itself. Okay, that's very nice. Okay, so let's have another one. A new, that's just a blank project. So just file, new, okay, blank project, and create. Good. So it will just be pop up here in the same window, so you can switch between the project very easy. And if you do this, that means if you wanna, for example, make copy and paste, slow again. You can make copy and paste between the projects, which is very nice feature. Okay. That's fine. Okay, we'll do it from scratch. That's fine. So we need AC source. So place again, component, and power source. We have also, yeah, we have the power source, AC source, but now AC source. Okay, and put this guy here. Then remember, we need also a ground. So just bring the ground. Okay. And it's very slow. I'm very sorry. Yeah. Finally. Good. And that's it. Don't need anything else from this list. And we need 2 resistors now. So place component resistor. Yeah, this guy. 1 kilo ohm. And we need another one, which is 1 ohm. Just pick again 1 kilo ohm, that's fine. Okay. And then you change later the value. We're gonna make it neat. So, yes, rotate it. Then take this guy, rotate it also. And they change its value to 1 ohm. Just one like this. Very easy. And then connect all these together. So we're gonna connect like this and connect like this. Oh. That's fine. Then connect this to this. And connect this to V1. Okay. Then we're gonna need oscilloscope. This is not good. Let's draw it. Oh. I don't like this one. So let's do it again. Yes. Going. We need now oscilloscope. So if you just follow the steps in experiment 2, the oscilloscope is, I think, number 4, oscilloscope. And we just need one. Okay. If you want to centralize everything, okay. Good. Now let's just follow the connections here. So this guy will go to this node in here. And this one will go to this here. And this one, it's actually the same point. Okay. If you remember the one node, they are the same point. And connect this guy to the ground. I'm assuming you are following me. Okay, because not to waste any time. Okay, that's good. Okay, so we have the connections. Okay. This 120 volt is very high, so let's reduce it to 10 volt. 10 volt RMS, which is approximately 28 volt peak to peak. Okay. You can keep it if you want, but it will be very, very huge for such a simple application. Okay, now we're gonna run. So simulate. Look, simulate here is not activated. The run is not, because this guy is still running. So basically, Multisim can run 1 second at a time from one project. So you must stop the running circuit or the running simulation in order to run another one. So how are we gonna stop it? From here, stop, or again from simulate and stop. That's a good one. Okay, so we're gonna simulate. Just run.
Do we change it to 1,000 hertz or do we keep it at 60?
Yeah, you can change it that as well. Yeah, you can change the frequency as well. I'm just choosing. You know, when I first doing it with the default values, it was ugly. Okay, I needed to work. The simulation is running, so we can do a change. So we must stop. Yeah, now we can run again. So I'm sorry for the interruption. So when I did the simulation for using the default values 120 and 60, it was ugly. I needed to make many changes inside the simulation. I'm sorry, the oscilloscope itself, in order to show the signals. Okay, I will show you now. I will show you. So yeah, let's now open the oscilloscope. Nice. So where is the other one? So you have here two signals. This one, and this is the one. Look at this one. This is the one which is really very small, very, very small. This is the one on the resistor R1. So the bigger one here is voltage across 1 kilo ohm, and the very small one, which is barely seen, is the one across the 1 ohm. Now we play with control knobs. on the front panel here, this is the front panel of the oscilloscope, just like any other oscilloscope, to show in a better way or in a more convenient way the signals. So we know that this guy is the second signal is on channel B. So we just change the voltage per division. Okay, so decrease it. Look. So you decrease the voltage per division, the signal will look larger. Okay. So you have the first one here. The bigger one is actually the one on the voltage on R1, and the smaller one is the voltage across R2 or RB, whatever you call it, which is 1 ohm. So this is actually a current also, can be considered as a current. Okay. Good. Now, if you want to measure, for example, this is out of the of our experiment, but if you want to measure yourself the voltage peak to peak, for example, of the frequency, this will be useful in future lessons. So you see this there is something here. So I don't know why it's not. The internet connection. So it's not responding. Something bad with my connection. So, anyways, if you guys are still seeing my screen, then you see this green stuff. This is actually something that you can move. Okay. Oh, that's not good. Okay, let's. I think the maybe done. Let's see. Good. Yeah. So these guys actually were here, but the connection was bad. So, anyways, so these two. It's not responsive again. Can move, okay. And you see this stops on whatever signal you want. Okay, now it's moving across the channel A signal. And so let's start by channel A. If you want to measure the peak-to-peak voltage, okay, just use these two. So now, this point, let's call it a pointer, for example. This pointer now is here at this exact point on this. So let's hide channel B. So you can hide any channel using the 0 here. So if you want to hide the channel B, just click on 0. Okay. So you have only now channel 1. So this pointer is pointing to this the top here, the top point, the peak, the top peak. And the pointer 1, look, this is 1, this is 2. There is 2 numbers, 1 and 2. And the pointer 1 is stopping here at the, the bottommost point of the channel A, okay, which is the voltage across R1. And just look at the numbers, look. So this means this point is minus 14 point whatever. And this point number 2 is stopped at plus 14 point something. If we move it, look, this is changing. If we move it, this is changing. Okay. So if you measure the peak-to-peak voltage, just make the 2 pointers at the 2 peaks, the topmost peak and the bottommost peak of the channel A. Then you take these 2 numbers and subtract them from each other, So 14 minus 14 is 14 plus 14 is equal to 28. Okay. If you want to measure the, you can do the same for a channel B as well. Now let's hide the channel A. So we press 0 here and just press AC here. Okay. We notice that this, I don't know what this point, let's say, is not moving with the channel A, not like the other one. So what you're gonna do is just click here, select a trace, then choose the channel P. This means the channel B on AC mode right now. So look, so now this is following channel B. So whenever I move, it will move with me. Okay, and whenever I move, this number here will change. This number, I'm sorry, number 2. So if I stop here, it's at 14 point something millivolt. And if I change this to here at the bottommost point on the curve for peak, then this stops at minus 14 millivolt. So the voltage peak to peak on a channel B, which is the voltage of the 1 ohm, is around, it's around 28 millivolt, which is 14 minus 14, 14 plus 14, 28 millivolt. Okay. If you want to measure the time or the period, again, right click, select source, and choose here axis. Okay. So you will be on the x-axis. So you can, for example, make something like this. So what is this point? Look here, there is a list called the time. So this number actually is a time at this point. If we move forward, it will increase. Look. Okay. And this time is actually, this point is actually at that time here. Okay. And by the way, yeah, you can just subtract them from each other, and this will give you the period of the signal. Okay. Okay, that's very good.
Wait, Professor?
Yes. Yes.
My oscilloscope graph isn't like looking like yours.
It's not looking like me.
It's not looking like your graph. Can I like share my screen and show you?
Yes. Yeah. Share your screen. Yes.
Okay.
Let me permit this for you because it's not. I will stop sharing my screen and let you share yours. So you can share now.
Okay. Okay, let me just figure this out. All right. And you can see it, right?
Yeah.
All right. And this is how mine looks. It keeps on moving and it doesn't have.
Yeah,
it doesn't,
that's okay. That's okay. So I will give you this trick now. No, keep it, please. Don't close. So, yeah. Just okay. Double click again. Okay, that's fine. So you see this single normal auto none just at the bottom of the controls to the right.
Oh, to the right.
Yes, choose single.
Oh, single.
Yeah, it will be slower now. Okay. Now we wanna increase. Of course, it's very tight, right? Because the time scale is not that good. So go to the time base, the rightmost knobs, rightmost.
Oh, right. Yeah.
You see channel A? I'm sorry.
Oh,
leftmost. I'm very sorry. Leftmost.
Oh, yeah. Yeah.
So you see time base, something called time base.
Yeah.
So in time base, there is something called the scale.
Yeah.
Yeah. No. The above one. scale. Yes, this one. Now we change, play with this. Increase or decrease. Play with this. You have these two arrows. Yes.
Huh.
Decrease it. Decrease, yes.
Oh, okay.
Hey, we done it.
Oh, okay. Okay, that makes sense.
Okay. So stop sharing right now and I will share mine.
Okay.
Well, that's good. Okay. So please stop share your screen to share mine.
Yeah, there it goes.
You didn't stop your screen.
I think I stopped it. I did, right?
Did you stop share?
Yeah, I stopped the share. Yeah, it should be done now.
Okay. Okay, so I'll share my screen again. But that was good. Thank you very much. Thank you very much.
Yeah, thank you for the help. Thank you.
Sorry guys for these connections, reconnect and stuff. I'm very sorry. Okay, but anyways, that's what we have right now. But that's good because it will shows you, the perfect world. If we are doing something using a real hardware, it will be, harder. Okay, it needs time, and also it might not work at all. Okay. So at least we know the exact behavior, what is the exact behavior should look like. Anyways, now that was out of our lab. This is not our lab to measure the peak to peak, but I'm just giving it because this is a good opportunity to do so. But in the future, we're gonna need this. Okay. Okay, that's very good. Just a little note. So what these numbers meaning? So for a channel B, for example, which is what we are currently showing, because we are currently not showing channel A because we put it in zero mode. So this means 10 millivolt per division. So any division here, any square, any division is actually representing 10 millivolts. Okay. So for example, this is maybe one division and maybe 0.4, something like this. Okay. So if you want to know the maximum, instead of using these pointers, these nice pointers, you can measure it yourself. So it's one division, maybe 0.4. So 1.4 multiplied by 10, which is around 14. Okay. 14 millivolt. And if we show channel A, the division here is 5. So how many division, for example? This may be 2 point something division, 2.9, for example, divisions. So if you want to know the maximum voltage, just multiply 5 by 2.9, which is approximately again 14, like what we measured using the pointers. Okay. And for the time base, so this means each division is representing 10 milliseconds. So each division, each square like this, each division is actually 10 milliseconds. So for example, for this here, this is one division, maybe 1.6 divisions. So the period of signal A is 1.6 multiplied by 10 milliseconds. Okay. Okay. Now let's go back to our lab. So the main purpose of using the oscilloscope is to draw the characteristic of Ohm's law linear automatically. Okay. So we're gonna go back to what's called XY mode. And where is XY mode here? XY mode is actually this guy here, B over A or A over B. Okay, so let's do the A over B. Okay, we need to increase the divisions. This is on 0. I'm sorry. Yeah. Then we're gonna make it more neat. Yes, that's very nice. Okay. So now we have Ohm's law automatically. Okay, it's perfect. You don't have to make it point by point or anything like this. Okay. Now, if we want to measure the slope, simply just look at the divisions, the x divisions and y divisions. Okay. So the x divisions here is 5 millivolt per division. So that means this square here, or this division here, is representing 5 millivolt. Remember, this is a channel B on the x-axis because we choose A over B. So A on Y and B on X. And we have for the Y, which is the channel A, we have 5 voltage per division. So this is the one division here is 5 volt. So, and to measure the slope, we need only 2 points. So for example, the 0 and 0 point, which is very nice. We have a point crossing on 0, basically because if the voltage is 0, the current is 0. So you must have a point crossing the 0 axes, okay, or 0 on this axis and 0 on this axis. And the second point, neatly, it will be this one, which is I'm pointing at. So the x at this point is 1 division. So 1 multiplied by 5, it's 5 milli. And remember, 5 milliamperes, because the resistor is 1. And the y coordinate of this point is also 1 division, and 1 division is 5 volt. So 5 volt divided by 5 milliamperes will give you what? Will give you 1 kilo ohm, which is exactly the resistor what we have in our circuit. Okay, so we could measure Ohm's law automatically on the oscilloscope. Okay, now you guys will, of course, in real report, just take screenshots. Okay, I will let you guys to do the same now. Okay, another ball for experiment. Save as and experiment to repeat. Okay, so let's proceed to the third one. Okay, new. Blank, create, and that's it. So in our third experiment, oh, I need to explain something now on the other screen. So let's go to OneNote to show you something which is really important. Okay. So this is the experiment that we just did, experiment number 2. Okay. And basically, what I can say, this experiment cannot be done in reality, in a real lab. You cannot do that. And the reason because with real oscilloscope, I mean. Because real oscilloscope has only one common ground. There is no 2 grounds. So look at here. So the channel A has a ground. Let's draw with another black, for example, yes. The ground of channel A is connected to here, to this point. And the ground of channel B is connected to this point. Okay. If this was a real oscilloscope, this is just a simulation. Remember this. The one that we just did is just a simulation. Okay. Then you will have a ground here and the ground here. So you have shorted the 1 ohm resistor. So you will read just zeros, something like this, just 0 on a channel 2 or channel B. So this is not actually a valid connection in if we're gonna make it on a real oscilloscope. Okay, of course we wanna be very close to what we're gonna see in real world. So in real world, the oscilloscope has a common ground, only 1 ground. So by default, the 2 grounds, the 2 negative terminals of the 2 channels are internally connected to each other. if you get a multimeter and you set it to the, you know, this beeping stuff that checks for the shorts, and you put the two terminals of the multimeter on these two negative terminals of the oscilloscope, you will hear the beep because there's a short. They are connected. So if we did this connection in real world, okay, then we're gonna make a short. Of course, it's unintentionally, but this is what's gonna happen. And RB will be shorted, so you will read 0. So we can't do the XY mode. You will, if you do the XY mode, you will see something like this. One line like this, the green line, this green line, and it's the vertical one, because you only have one signal, and the other is zeros. Okay, so let's now do the practical setup that you can do in reality, that you can do with the real oscilloscope. So let's go to another page here. So we have the same stuff. You have this guy R equal to 1 kilo ohm or 1 ohm or 1 kilo, 1000 ohm. And you have this R, let's call this R, and this is RB as usual, which is 1 ohm. And you have here your sine wave generator. Okay. So, and the oscilloscope will be connected. Let's draw it first, then yeah. So we have here the oscilloscope, our oscilloscope, A and B, positive, negative, positive, negative. This is real one now, okay? We wanna simulate the real stuff, something very close to the practical world. So you're gonna connect channel A, the positive to this point, but the negative to the common ground of the circuit. Wow. Now it's gonna measure the two voltages together. The voltage on RB plus the voltage on R. And for B, we'll do the normal thing. So for B, let's draw it with another color just to differentiate. The positive will be here, as usual, as we did in the experiment number 2. And the negative will be to the common ground. Now the two grounds are connected to the same point. That's okay. That's very okay. Okay. So a channel B will actually still measuring the voltage across RB, which is equal to the current because the resistor is 1 ohm. But the channel A now is measuring actually this whole voltage. So VA is equal to VRB plus VR. It's not only VR, but since RB, I'm sorry, is much less than R, this is 1 ohm, this is 1 kilo ohm or 1000 ohm. So VA is approximately equal to VR. Okay, so since we choose, so I choose R equal to 1 ohm, very small, very smaller than R, 1 kilo, because of this. It has a reason. Because for the practical stuff, you must have this one with a very low value than the other one, the one that you're interested in, which is the 1000 ohm. Okay, so the voltage on A now is approximately equal to the voltage on VR, which is the 1000 ohm. But still, the voltage on B is still equal to the current because R is 1. Now we have a condition for the correctness of this experiment. The condition is, let's draw the condition to get accurate result. For accurate results is that RB should be much smaller than R. Okay? And this is obvious here. This is 1 and this is 1000. Okay? Even with voltage divider. So this is a source, our source here. So VR is equal to V, the source, VS, let's call it VS, multiplied by R over R plus RB, but R is 1000. This is 1, so this is 1001. It's which is approximately equal to 1. It's 0.99 something like this. Okay. So we're gonna repeat what we have done in experiment 2, but now we're gonna change the connections of the oscilloscope to be more close enough, or yeah, to the practical world, to the practical setup that you're gonna do in a real lab with a real oscilloscope. The real oscilloscope has only one ground. Okay, it's one common ground. So the ground of channel A is exactly the same as the ground of channel B. Actually, we in the practical world we can even not connect this at all. It's fine because the two grounds are internally connected, so you don't need to worry about it. You don't need even to connect it because the ground in channel A already did that for you. Okay. So let's do the just So let's now do that. Okay. And instead of drawing everything from scratch, you're gonna go to the lab in here, just to close the oscilloscope, close the measurement stuff, and try. I don't know how can we get, yeah, zoom in and zoom. We have to zoom in. I will make copy and paste. That's what I'm gonna do. Copy. And go to the design here, make a paste. Good. Choose the locations and click. Left click. Now let's do the practical measurement. In the practical world, you can't do that. Okay. In a simulation, you can do as well as long as this oscilloscope has no common ground. Okay. So I'm gonna connect. Delete. Yes. I'm gonna connect. So the channel B connection will be the same, but I'm gonna connect now channel A to ground to the same ground as the channel B, which is 1. Now channel A is measuring from this point to this point, all that voltage, just like what I showed in the one node. Okay. Now let's do the experiment again. Let's run. We shouldn't see any difference because they are very, R1 is very larger than R2, which is 1 ohm. So you will not see, a real difference. So let's open the oscilloscope. It's exactly the same, right? This was the last figure that we show in experiment 2. So if you measure, you will find also 1 kilo ohm, approximately, of course. Okay. Now you will do that. You will take the screenshot. Then you will change the resistor to 2 values. One is one is 10 kilo ohms, much larger than 1 ohm. Okay, and then you change the resistor under interest to 0.1 ohm. Okay. And let's see what let me see what you're gonna have. Okay. I will be with you. We have still 10 minutes. Okay. At 12:30, I will just finish. That's fine. Then you can, if you didn't finish, just try to finish today. Try to finish just after, if you don't have something after this lecture, because you are in the mood. You have, you are now familiar with Multisim. Okay. So it's easy. Just try to finish it after the lecture, if after the lab. if you didn't finish by 12:30. Okay. So I am with you guys until 12:30. At 12:30, I will see if someone has a question, if I can answer. Okay, then we're gonna finish.
We're changing the 1 ohm to 10,000, or is it a 1,000 ohm?
No, it's a 1,000 ohm.
So we're gonna change that one to 10K and to 0.1.
Yes, that's right. But
Okay, thank you.
yeah, so let me. So if you see, it's called R1. Okay, and if we look at the schematic here, the circuit, it's R1. So it's obvious it's clear from the manual. I'm saying R1, and R1 here is the one under interest, which is 1 kilo ohm. R1 here is R that I was explaining. I'm sorry for confusing the symbols. And R2 is R or RB. Okay, this is R and this is RB. So every time I'm asking to change R1, which is R. So all the time, the 1 ohm will still be 1 ohm. Okay. I want you to do the 10K and 0.1. Then write a comment, because at 0.1 you will see something bad. Okay, so I wanna know. Just write to me